Hello, everybody. Thank you for joining us today. You are now part of the 250 people worldwide who have registered to this webcast powered by Yole Developpement. This webcast will deal with artificial intelligence computing for automotive. My name is Julie Robert, and I am Marketing and Communication Officer for Yole Developpement. Before we start the webcast, let me give you some basic information on this online event. You have the possibility to submit questions during all the webcasts. You can use the Ask a Question window at the bottom of the screen. We will answer as many questions today as we can, and for the remaining ones, we will follow up with you via email. Concerning the materials, please note that the presentations are already available and that can be downloaded from the resource section of the platform. Furthermore, you will receive tomorrow an email with the links to the recorded webcast session. To introduce you the company, Yole Developpement is a market and research and strategy consulting company providing marketing, technology, and strategy consulting services. Our field of competence are numerous and are covering photonics and sensing, power and wireless, and semiconductor and software. During this webcast, I am pleased to welcome Yohann Tschudi, Market and Technology Analyst at Yole, and specialist of the computing and software industry, as well as Stefan Cordova, who will present Kalray vision of the AI computing for automotive market. So let's start the webcast. Please, Yohann, the floor is yours.
Hello. Thank you very much, Julie, for this short introduction. Thank you, everyone, to be here today. I hope that everything will go fine in this webcast. We are in tough conditions today, but hopefully we will be able to get to the end correctly. So on this slide, I'm presenting the agenda of the presentation, of the Yole presentation. We will define first the scope. Then I will make a short explanation of the evolution of the computing industry, so from CPU to accelerations. We will enter in details in terms of on automotive, in terms of levels of autonomy. I will make some forecasts around the artificial intelligence computing hardware that will need to reach the different levels of autonomy. I will try to explain what are the technology and the market trends behind all these forecasts, a short description of the ecosystems and the battle around this race for autonomy, and a short conclusion. So let's begin with the scope. What we have done since 3 years now at Yole is to try to understand the impact of artificial intelligence on the semiconductor industry. And we have made several reports around that on the consumer, smart homes. And here we'll present you the last analysis we have made for a report that will be released soon. Around the impact of artificial intelligence on the computing hardware for automotive. So artificial intelligence is present in two different segments in automotive. One is for autonomy and the other one is for infotainment. In this presentation, I will focus specifically on the autonomy side. So a short explanation on what has been the trends the last 15, 20 years, from general applications to what we have today, meaning neural networks. We have observed a shift of the performance focus for the semiconductor industry from general application with general workloads, where we have a lot of integral operations that tend to be sequential in nature, and the best chip to do this operation were CPUs for long times. CPUs have a few powerful cores that tackle computing tasks sequentially. On the other side, on what we've seen to what we're seeing today, or at least for the last 10 years, we are in neural networks, deep learning workloads where we have floating point operations, and this tends to be parallel in nature. The best chips that have been suited for a long time were GPUs, which are hundreds of specialized cores that are working in parallel. So parallelization is key, and it explains why GPU are so popular for deep learning workloads. But if we try to go further, in this explanation of this understanding of trends, we are seeing from 3 years now a shift from GPUs to dedicated ASICs to accelerators. So we went from scalar processing with CPUs that run at clock speeds in the, let's say, giga-megahertz range. And if we want to do some parallel computation for our vector operation, we see that might take a long time to execute large matrix operation via sequence of scalar operations. Then we entered into the era of GPUs with vector processing and the same operation that are performed concurrently across a large number of data elements at the same time. And today what we see is graph processing, and this runs many computational processes. This calculates the effect of these vertices on other points and the overall processing works on many vertices and points simultaneously. We don't need a high precision to do that. And the names, there are a lot of marketing names. I just point out some there. What we have chosen at Yole is to name that accelerations, or accelerators, but you will see neural engine, you will see tensor processing unit, neural network processor, intelligence processing unit, deep learning accelerators, etc., etc. Each company has its own name for this type of unit or this type of chip. Just to remind that all along this presentation, I will call that accelerators. Let's enter in the automotive industry. If we look at the technology times market penetrations along time, it's the plot we have here, we see that ADAS vehicles are growing and still increase for the next 10 to 15 years slowly. It's market as usual. I will not speak about the COVID effect for now. There will be some dedicated slide later. For robotic cars, though, what we see, it's more about exponential penetration in the market and technology expectation too. And here we have all the characteristic of a disruptive technology. So the speed of the technology changes double every technology shift, and autonomous vehicles will at one point, we expect to see that in a few years from now, will at one point will be a main transportation for many people. So what we see today is that 2020 is or will be the first commercial implementation of autonomous vehicles through Waymo, for example. On slide 9, I'm presenting just this disruption case for robotic, where we see these two distinctive paths for autonomous vehicles. So on one side, we have what we call ADAS vehicles that are characterized by levels of autonomy from level 1 to level 5. And on the other side, we have robotics vehicles that are increasing their autonomy not through more functionality, but by getting more and more speed. So today, if we are looking at robotic vehicles, they are in designated place or designated areas at limited distance and let's say at medium speed. But the objective to reach this robotic mobility as a service is to get at any speed anywhere. This objective is the same for ADAS vehicle, for the historical players, for all this automotive industry we already know. But they are increasing their autonomy by adding functionalities to that, and it's why we are seeing this level 1, level 2, level 2+, level 2++, and level 3. Just a short remark on level 3. It's very questionable today. There are some OEMs that even decided to not go into this level 3 and to directly tackle the challenge of level 4 or level 5. And this is because there is a shift in the responsibility of, in case of accident, is it the driver, is it the company? And in level 3, there is this shift between both of them. So is level 3 relevant? Is level 3 will exist at one point? At Yole, we are not really sure of that, and there is a lot of technology aspects too that are entering into account that make this level 3 very, very difficult to establish. So just a small word on our work the last month on the COVID effect and on the impact on the automotive industry. So this is the results we have done last month. We have done this work based on the production level, at the production levels. So what we can see is that for this year, we expect a decrease in production on around 30%, and the next 5 years, it will increase slowly to get back to normal. So the impact of COVID has a huge impact today, this year, and probably next year, and then it will be probably go back to normal very slowly. So on this, and if we look at levels, we expect that by 2035, cars with autonomy level 3, 4, 5 will represent 25% of global production. The rest will be level 1, 2, and 2+. In terms of research and development for autonomy, I will explain that later in one slide dedicated to that, the impact of COVID, on this research and development. I will explain that a bit later. But for sure, we can imagine that this COVID, the COVID impact will have a huge effect on the level of cash that all these companies will have for all the research and development for electrification and for autonomy, that are the two biggest trends in automotive today. So let's focus now on the artificial intelligence aspect. And what we have done is to look at, what will be the type of chips that will be used for artificial intelligence, and what will be the ISP, the penetration rate, etc., etc. And here, what you can see is directly the result of this analysis. Artificial intelligence based on images. We have done this work based on the numbers and the type of cameras that are implemented in the cars, and that will be implemented in the next 5 years in cars. And this will generate a total volume of 67 million units. So that means that for artificial intelligence in 2025, 67 million unit chips will be dedicated to do this task. And this is only for ADAS vehicles. I'm not counting robotic vehicles there. So what is the most important assumption is that what we see and what are the trends for the next 5 years, at least, is that we consider that for one type of camera, we have one chip which is used. So we can find multiple chips in one car, but fusion of inputs from multiple types of camera is not considered for now. If we have different types, meaning that if we have multiple cameras, it's always one chip per cameras in the cars for now. And it's something that we can see today, but there is a trend. And if people are asking the question, I agree that there is a trend of centralization with one computer, like in the car, like we can see in Tesla, for example, with their FSD chip, our solution proposed by NVIDIA, which is a centralized platform that will be able to manage all these cameras inputs and run the functionalities that are asked. In terms of revenues, what we see is that the artificial intelligence market has just started. Okay, it has been implemented by Tesla through this full self-driving chip I just talked about, and what we saw today, what we see is that artificial intelligence in automotive for autonomy is just Tesla that is taking care of it for now. Okay, so what we have done is just to look at what Tesla is doing, and it's why we have on this plot the COVID-19 impact on Tesla production that has a direct impact on the revenues produced by artificial intelligence computing hardware for this year, 2020. And then we expect in 2021, so next year, that all other OEMs will integrate the solutions that will have artificial intelligence embedded in it through, for example, an accelerator. This is what we expect for next year, and this is where the inflection point here. So think about 2021 for the beginning of artificial intelligence for the whole automotive industry. In terms of number, what we have is what we compute is a revenue for 2025 to reach 1 billion, almost 2 billion in 2025. In terms of technology trends, from level 0 to level 2++, we have on one side, and robotic vehicles on the other, we have two different strategies. So for level 0 to level 2++, they are differentiating mostly by improved functionalities, such as AEB or TGA or lane keeping assist, LKA. And on the robotic side, as I said, the full autonomy was first realized in closed area and at low speeds. And the next goal is to do full autonomy everywhere at any speed. But what we observed is that these improvements are realized or will be realized thanks to the introduction of artificial intelligence algorithms and its related hardware. So implementation of AI, there is two different trends following what we have been done in consumer applications. So what we have seen in smartphones, for example, with the integration of the neural engines in Apple 10 3 years ago. What we expect and what we see is that the implementation in SoC for ADAS, in system on chip for ADAS, or standalone chips of acceleration. And you will multiply this number of chiplets to get the computing hardware for robotic players today and for the next few years. If we look at this example, we can focus and we can look at what Intel Mobileye's next solution, and I know that BMW, for example, has presented yesterday its roadmap for using Mobileye EyeQ5. And what we see is that between the EyeQ4 and the EyeQ5, not only the performance of the chip is different, is a factor 10, but there is this difference of performance is done through these accelerators, what they call the deep learning accelerators, and they introduce that in their next solution in the EyeQ5, which has already been tested by OEMs, and that will be in production next year. If we look even at the NVIDIA solution, so NVIDIA is a very interesting solution because they are selling GPUs, and GPUs are already pretty well suited for artificial intelligence. But even though, if we look at the Xavier's SoC, which is announced for level 2++, and that will be probably in production next year too, we see that even if they are selling GPUs and proposing GPUs, the next generation of SoC for ADAS will embed these accelerators that they call to DLA. So this trend of acceleration is seen from all the players. All the players are using and they want to integrate this type of acceleration because there is this huge need to introduce artificial intelligence in the autonomy software stack. And everything is combined, software and hardware, hardware and software. Here you have a mapping of all the chips from level 1 to robotic and level 4 and 5 from 2020, 25 to 2020, 2025 and 2030. And what we see, the trend we see is that there is an ADAS computing race, and the goal obviously is to get a higher performance for minimum consumption. And the next battleground for the ADAS is now. It will be in the next few years between level 2+, level 2++. And as I said at the beginning, level 3, we are not sure that level 3 will happen at one point, but what we see is that we went from 0.1 TOPS per watt to 1 TOPS per watt, and the next step is to get to 10 TOPS per watt. And that can be achieved thanks to the addition of this acceleration, thanks to the introduction of artificial intelligence algorithms for recognition, for example. So today, ADAS computing is using chips between 2 to 20 watt range, and robotic vehicles are using chips above 100 watt range. in terms of evolution of this computing hardware, here you have the type of computing behind each type of radar. So on the first line, you have the levels and the functionalities associated to each level. On the second line, there is the table representing the technology penetration of each type of computing hardware. So in orange, we have a microcontroller or CPU. In light orange, we have the FPGA. In green, what we call vision processor. So vision processor is it's Mobileye vision processor like, for example, and centralized platform as it is seen for Tesla or for NVIDIA, for example, or what NVIDIA is proposing. So what we expect is that from level 1 to level 5, we will have this centralized platform, which doesn't mean that it's just one chip. For today, this is the case, but if we associate 3 or 5 or 5, 3, 4, 5 or 6 Mobileye, that can be a centralized platform too. Okay, so what we can see is that we will go more and more through this trend of centralized platform. So this is not only because we need more computing power, but there is a huge trend too in the automotive to reduce the number of ECU and to be able to have just one module that will take care of all the computing aspects in the automotive, at least for automotive. For business model, we see something very classical. We have 4 different business models. We have the car manufacturer on one side, so the OEMs. We have the people that are building the brain of the car, so for autonomous driving, software and IP hardware. We have all the aspect of electrification too, for battery and powertrain manufacturer. They are turning cars into electric powered systems. And we have the people that are building cars around the idea of making a service of mobility, named mobility as a service. And these are mainly pushed by tech giant technology, such as Uber, Lyft, or even Google through Waymo. And what we see is that the major value flow will go to this service provider, and more car manufacturers are looking at this business model of mobility as a service with a good eye. Let's say this like this. Okay. Finally, if we look at the ecosystem, we have 2 different ecosystems. We have ecosystem for ADAS vehicles on one side and robotic cars on the other side. Just because for ADAS vehicles, the players are not the same, the ASP pressure is not the same, the technologies are not the same than for robotics. This is true for computing, but this is true for sensors too. In both of this ecosystem, we see that the supply chain are organizing. So ADAS ecosystem are built around historical automotive OEMs, and supply chain going less and less through tier ones. They are still there. I'm not saying that tier one are not part of this autonomy trend, but they are directly OEMs are directly discussing with computing players, with software players. For robotic vehicle ecosystem, they are built around full stack solution partnerships. They are built around partnership, and this is where this is important, such as proposed by NVIDIA or Apollo. So this partnership, this is because the path to full autonomy through robotic cars is tough. There is a lot of complexity to get from scratch to full autonomy, to build a car from scratch to full autonomy. So as I said, there is 2 main ecosystems, with NVIDIA, which is leading the computing hardware ecosystems, and on the other side we have Apollo, which manage a huge ecosystem and which is very promising. Just for to look at when we look at the impact of COVID, we have analyzed what was the positioning of each OEMs, okay, their level of investments, their level of autonomy, and we can see that we have 3 types of strategies around 4 types of players. So if we look at the different players, we have Tesla, for example, which is developing the full solution by themselves, and this. Looking at the COVID effect, the COVID impact, we expect that Tesla will not be so much impacted because they are increasing their autonomy step by step, and this is already a huge focus in their strategy. Electrification and autonomy, this is what they are already focusing, both of them. For some OEMs that want and that are developing their own autonomy stack, but they are using the silicon provided by the computing hardware player on the top. We see that we expect that COVID impact will make these advancements that will be slower. Okay, so we do not expect maybe 21 will be the first year, but it will not be as impressive or as important that we expect last year, for example. And for other players that are already using full solution provided by computing hardware company and software, and that are not doing their own software, this will be much more complicated for them. So just to be clear around this, what we see is that all the cash which is lost today will not be burnt tomorrow in autonomy. For these players, for most of these players, at least in Europe or in Japan, the main budget or the main will is to tend to electrification. That is the first will for these players. And autonomy came in second place. So what we expect is that some players will simply stop this race in autonomy, and that they will use full autonomy or functionalities that will be fully provided by computing hardware player in a few years. So just to conclude on that, and the key points around this, levels of autonomy should not be considered as incremental as we can see. We have not level 1, level 0, level 1, level 2, etc. We have level 1, level 2, 2+, 2++. So this is because the underlying technology are evolving, thereby requiring intermediate levels. This is very linear, it's not incremental. Level 3 is questionable as liability and regulation are not included. So I repeat that many OEMs have decided to skip this level 3 and are working directly on level 4 or 5. I want to stress too on the point that ADAS vehicle and robotic vehicles are two completely different markets. Ecosystem, technology, ISP, objective, business model, everything is different. And the impact, the entrance of artificial intelligence through acceleration that enables the increasing number of functionalities, and this is parallel to the increase of number of sensors around the car. For ADAS vehicle, AI has been introduced since 2016 in Tesla vehicles, and last year they have begun to introduce their own dedicated platform. However, as accelerators will be embedded in next generation SoC by every computing hardware player, Xilinx, as I showed, Xilinx, NVIDIA, Ambarella, Toshiba, TI, and obviously Mobileye. So we will see that the beginning of the entrance of artificial intelligence in automotive will probably be 2021, and that will spread very quickly. For robotic vehicles, AI has been in use for years, used based on GPUs, mainly provided by NVIDIA. And because we will need fusion of multiple inputs, and it's already in place for robotic vehicle, a combination of GPUs and accelerators in the same SoC or as two different chips will be used in the future. Finally, I want to stress on this point. The application is key. Focus should not initially be on the performance of power, but on the application technology. So a lot of warning I want to make for this, the warning I want to make for this presentation is that do not forget software. The software stack to make the chip efficient, and obviously the algorithms that make the automotive autonomous. So this is the two different software that sometimes times, and I see that in the industry there is not a lot of stress on that, and a lot of people are looking more in terms of performance per watt than on the software stack. And for us, it's a mistake. The last 3 points, just to keep clear on that, Tesla was the first in introducing AI and is driving the AI hardware trend from computer vision, AI with GPU to accelerators. Accelerators are keys for computing AI algorithms, and all along the value chain, software should be the focus for success. Thank you very much.
Thank you, Yohann, for your presentation. We will now continue with Stéphane Cordova, who will present Kalray vision of the AI computing for automotive market. Stéphane, the floor is yours.
Thank you, Julie, and thank you, Yohann. Good afternoon, everyone. Good morning. So let's start by a brief introduction of Kalray. And so Kalray is a fabless company designing a very unique a new type of Manycore processor for intelligent system. So we have spin-off of the CEA, a well-known research lab in France. So mainly located in France. Kalray is mainly located in France. We have office around the world. We are about 100 people today. We are a public company with industry market leaders as NXP and Renault Nissan Mitsubishi Alliance for automotive industry, and also Safran and NVIDIA for aerospace industry. So Kalray has more than 10 years experience and know in the field of Manycore technology now. So we are just released our third generation processor, Manycore processor, early this year. And we have 30 patent families to protect our technology. Today, Kalray is focusing on automotive and data center for our products. So what are an intelligent system and why are we targeting this market? So the processor industry has seen three major revolutions, basically. So in 70s, with the computer and the single processor, basically at that time, increased performance, you had to increase the frequency. But the higher the frequency, the higher you consume. Then in the 90s, we have seen the emergence of the mobile phone and importance of power consumption. So industry moved to completely new architecture. So we all thought that the computer processor was perfect match with the mobile phone, but in fact, it happened it was not true, and a new technology arrived, which were really focusing on the power consumption. So now the era is changing, and this is the era of data, the need of analyze on the fly beyond of data and make decisions. And this is what we call the intelligent system. And these intelligent systems are largely based on artificial intelligence. So this type of application require, and it was well mentioned by Yohann, a new type of processing capability, processor, a new type of accelerator. And that's really the focus that Kalray is having. What is interesting is at the same time, So then let's explain what is an intelligent system to, so if you want to explain to a kid what is an intelligent system, the most easy way to explain is that you take example with an autonomous vehicle. So it is, it's drive alone, and it can take some decision on its own. And what is this is very interesting, and it was been well covered by Yohann, is the automotive industry is changing, and this push to think differently the way that you are going to let's say to create the new car. So, and this is the first example of, and this was mentioned also by Yohann. So car makers also become a service provider. So he has to think about the car as an open platform. He has to think about the software ecosystem or the application ecosystem. So it's really, it is a different factor for a car manufacturer to bring values and services to the customer. It's very similar to mobile phone industry, actually. Then the autonomous car also push to have much more data, to have much more application, and to have much more functionalities. So today in the car data, we are thinking about terabyte per day generated by a car, by a single car. So it's obvious, it's pushing for more performance, it's pushing for more software, and it will complexify a lot the system. So the performance increase will be mostly driven by the capability of the car to drive alone. And this rely, of course, and this is the theme of the today webinar, is it's really rely on AI. And this is the only way to drive correctly a car, is to use massively artificial intelligence. But it's important because we are in the vehicle and we have passengers in the vehicle to make sure that this is not going to jeopardize the safety and the security. And you have to come with new technology, of course. You need new technology for AI. You could take technology from data center, but it does not work because it needs to be safe. So you really have to have a specific technology for the automotive industry. So what is a new generation vehicle, and what does it mean? So today, vehicle, as it was mentioned in the previous slide, you have different complexity from level 2 to level 5, but even if the complexity is different from the level of the product of the car, it requires always the same and similar application. So you always need to have a large or different type of applications. It goes from a decision, to take decision, it goes to a path planning kind of application, then goes to perception largely based on AI or even on computer vision. So, but it's not the only thing that you have to take into account with a new generation vehicle. As I said before, it should be open in the sense that you have to incorporate new type of application, and in the really easy manner, in the sense that it could be a software upgradable feature. And the example of Tesla Autopilot it's perfect. They can upgrade the feature of the car just by upgrading the software, or they just upgrade the car, upgrade the hardware and giving more features, but without changing the car. So it's completely new concept than before. And this is important because the car needs to be open, but needs to be flexible. And KaNN, we truly believe open platform is a key for this market to deploy. That's a real differentiate factor for car maker. Today, car is already very complex, and I think today an average high-end car is having about 50 to 100 processor ECUs, and any new functionality that you want to add means that you have to add processors. So we understand, with discussing with our customer, car makers want to change this. That's critical for them. So they are thinking about more centralized functions in order to reduce the complexity of the vehicle. So if you also consider a traditional car maker, this means that you have a lot of models. And from high-end to the low-cost vehicles, you have many models. Of course, you can't afford to have one architecture and one software for each model. You really need to think about scalability and flexibility of the architecture in order to address the low-cost model and the high-end models. So that's very important as well. And on top of that, you have the usual and the standard and obvious elements that you have to add in your car. Of course, performance. We all speak about performance. Yohann also talked about that a lot. Performance is very important, but cost is also very important. today we are speaking about an industry with high volume. So the cost is very important. So you can't afford to have a lot of computers and very expensive processor in the car. You really have to take into account that. And of course, having more services and more performance does not mean that you need to play with the safety and the security. So again, and this is an important message that I want to add, it's every time the safety must be put at the first priority. So if we zoom a little bit on the key challenge of that we believe are critical for the car industry, the first is performance, of course. An intelligent car needs to have a lot of compute power. That's clear. And we are speaking today for probably the most important, about 150 TOPS, 350 TOPS. So usually this is what we can see on data center, but absolutely not in the car. So it's definitely something that has to be changed. You have to find technology and processors that are capable to do this level of performance without impacting the power consumption or the safety. And if you want to increase the performance, but you have already a very complex system with a lot of computers, and it's already very hard to upgrade this system because you have too much computers. There is no way to increase performance in such system. So when you want to increase performance, you have also to think about aggregation, centralization. You have to reduce number of computers in the car. This is mandatory. So the job of the system architect is become very hard in the car OEMs or Tier 1, because they have to bring the right level of performance to execute the software that you want to execute in the car. But you have to reduce the number of computers that you have in the car. So of course, this person has to find the right technology which allow to aggregate and simplify the system by adding, by merging function onto a simple number of processor or computers. So this is the Kalray architecture. So this is our MPPA Manycore processors. This is the brand new Coolidge processor, which has recently been announced. This processor is a free from interference and deterministic Manycore processor. So it allows, by architecture, to run multiple applications on it. And it is based on different type of architecture. So what we have done at Kalray, we have designed our chip in order to take the advantage of the DSP for all the time predictability and the real-time processing, and take the ability of the CPU and ease of programming of the CPU. And we merge it in our processor. And this is what we have been achieving with our processor. This processor, sorry, something is wrong with my slide because there is something missing, but okay. So this processor is an 80 cores processor with 80 coprocessor. So you have the capability with the 80 cores and the 80 coprocessor to run a wide range of applications, starting from CNN, but also moving to a very complex mathematical acceleration, and even having several CNN running on the same chip. So if you want to see how we can use this architecture, it's simple. So each C, it's a cluster. A cluster is 16 cores and 16 coprocessors. Each cluster can be seen as an independent computer unit. So each cluster can run its own application. So you can imagine that with this kind of architecture, it's quite easy to port several applications on the same processor, using the capability of the cluster and the spatial partitioning of the cluster by moving different applications and running different applications on the device. So in this case, we have typical application that you can find on the car. So big CNN which can do the segmentation of the road, for example, and then in addition, a computer vision which can do the pre-processing of the camera, the post-processing, and then you have a path planning which helps the car to select the right trajectory when detecting an obstacle, for example, and then another CNN which can be used for road sign detection. That's the basic thing that you can have in the car. And this is, for example, this is a use case that we are implementing with a customer today. So this is nice because on this, in fact, with this processor, you can save a lot of other processors because each function that are running on the MPPA today are running usually on different processors. So here they can run independently and simultaneously on the same chip. So you start to think about the way to simplify the system by reducing number of processors. And what is important, we spoke about AI a lot. This is the theme of the webinar, but AI is not everything in the car. So you must have also the capability to run other applications in the system. So it's very important to have the ability to accelerate other applications than just AI. So computer vision, path planning, mathematics are very important applications that needs to be accelerated also into the car. So how we do that? And so to allow software developers to implement such complex system on MPPA, so we are at Kalray, we have defined a CAF. CAF is a Kalray acceleration framework. It's basically a simple way to program the Manycore architecture and give access to the developer to different way to program the machine. A direct way, this is accessing to what we call direct programming. So you can access directly to the standard programming model, C, C++, OpenCL. So very standard, no proprietary language here. Or you can access to optimized library, again, standard libraries, which can accelerate computer vision, which can accelerate mathematical, so with a BLAS or LAPAC, and then CNN libraries to accelerate any type of CNN. So this is interesting because this framework allows to really build your system onto the chip. And it manages the faculty and the capability to have, thanks to the spatial isolation of the MPPA, to play with the function and map the function where you want on the processor. And this is interesting because this framework is also valid. It's perfect when you have an existing processor in the system. So basically today the car has a host processor. They have a legacy, which is usually based on x86 technology or ARM technology. And they are running the main application on this device. What they need, because they need new functions, they want to introduce new function or new services. They want to accelerate. So they can use one or several MPPA processor and offload all the compute-intensive function onto this processor without changing the main application. You just scale using standard API and standard programming model. You scale the performance using an external chip, which is in this case the MPPA. And of course, with the guarantee that as this processor is respecting automotive certification, you are also ensuring the overall safety of the system. So of course, we can't speak about AI without explaining the tools that allow AI developer to develop on a machine. And as every other processor vendor, Kalray has developed its own tools, which is called KaNN, which stands for Kalray Neural Network. So as you can see, by the way, we like the letter KaNN because we used to use this letter every time for our product. But KaNN is our solution for machine learning programmation. And it has two functions. One function is a code generator. So it takes information from the standard framework from TensorFlow Café and generate a code which can be directly executed on the MPPA processor. Or it is also libraries which propose to the end user, to the developer, to have access to an optimized libraries of machine learning. So this is very powerful tools to prototype directly your machine learning problem onto the final target, which is the MPPA. We mentioned previously, I have put it several times in my presentation, the scalability. And this is very important point. Again, if we want to propose to a customer the capability to keep same hardware architecture and same software architecture amongst the full product range, the full car models, this is going to simplify the life of our customer clearly. And today, it's very important to be able to reduce investment on developing new architecture or developing new software because you are changing models. And that's the big issue of our customer today. And they really want to solve it by having a scalable platform, an open, scalable platform. Fully software programmable platform, but scalable means that you keep the same software over your product range just by adding accelerator. And this is exactly the way that we have designed and we have thought our product is from a cluster IP, which can be integrated in a third-party SoC vendor, for example, going to the single MPPA processor, which can be used as an accelerator to an existing host processor, to even a multiple processor, multiple MPPA processor to, I don't know, to arrive to a range of 400 TOPS performance if you really want very high number of TOPS or number of performance. So this is very interesting way because you save the software development with that. You just use the natural scalability of the technology, of the processing technology to scale up your performance and adapt your performance to the models, the vehicles, and the model that you want to design. And this is exactly what the way that NXP and Kalray are working within our strategic partnership. So as you know, NXP is one of the leaders in car industry with a strong know-how in this field and in the safety area. So what is interesting within this partnership is that with the next generation of NXP Blue Box autonomous driving reference platform, it's pretty well, I mean, this is well known, including the S32 family of safe automotive processor and also the Layerscape automotive grade processor. You add, you integrate the Kalray MPPA processor, and you provide a very scalable, safe, and fully programmable solution to your customer. So with both companies, we are able to have a complete solution addressing the whole range of car models. Having the performance, the scalability, the programmability, of course, and of course, the last but not least, the safety. And this is today a pretty unique platform that you can have. So my conclusion is, this is my last slide. So this is the zoom of our Coolidge processor. So we announced the Coolidge at the CS this year. And we believe that with this new processor, this new MPPA technology is the perfect match to address all the new challenges of the car industry that we have covered before. And this open platform allows, as it is a CPU-based platform, it's simple to program and it brings very high performance. Coolidge include dedicated coprocessors, which are very efficient for CNN acceleration or for computer vision acceleration. So this allows us to achieve performance on 25 TOPS, 50 TOPS, and even 100 TOPS within the same processor. So that's very interesting. All this with an ASIL B level processor, which is available now on the market. Thank you very much for your time. This was my last slide.
Thank you, Stefan, and thank you all for this relevant presentation. We are now going to wrap up with the Q&A session. As we are quite out of time, we will only answer one question per speaker, and we will follow up via email for all the remaining ones. So the first question is for you, Yohann, regarding the automatic marketing trend. Based on your presentation, the sales recovery of the loss in 2020 will be in 2022. What about expectation in 2021 device for automotive sales?
That's a tough question. So what I've shown is the production. It's not sales, okay? And sales are a lot depending on sales of automotive for the automotive industry are a lot depending of psychology, of consumer. So what we expect is that for next year, there will not be a lot of sales. We are still work in progress, but we have compared, we have looked at what happened in 2008, even if the crisis was not the same at all. We try to understand what was the behavior 12 years ago, and we have seen that the sales have restarted almost 2 years after the crisis. So it's what we quite expect today, and that will be for automotive and all the devices behind. Thank you.
Okay, thank you, Yohann. For you, Stefan, from your presentation, the attendee have understood that you can execute multiple applications. Does it mean this could be application with different level of safety?
Yes, absolutely. So, of course, the spatial partitioning of Kalray processor allows this repartition of application onto the different clusters. And yes, definitely each clusters can run different application which can have a different safety level. And we have the capability to even isolate a cluster from the rest of the chip, which allow really severe partitioning between safety application.
Thank you, Stefan. So the webcast is now over. You will soon receive email with the link to the recorded session. Also, please free to share the presentation with your colleagues. And finally, please let me remind you that you can find all our reports on our website, i-micronews.com. Do not hesitate to contact us if you have additional questions. You can find our contact details on the last slide of the presentation. Thank you all for joining us today, and have a good day.
C'est fini?
C'est bon.
Vous êtes toujours là?
Il y a toujours un petit temps de latence, c'est pour ça qu'on attend.